We talk about space travel all the time, but what would it actually take to reach Pluto? Or what about our neighboring star, Proxima Centauri? Today, we're going on a journey through space and time to answer one of the most fascinating questions in astronomy. How long would it actually take us to reach these distant worlds? If you're curious about these mysteries, make sure to give this video a like. Your support makes all the difference. Now let's begin. To understand the challenge, we need to talk about distance. Not the kind of distance you measure with a ruler or even a really long measuring tape. We're talking about cosmic distances measured in astronomical units, light years, and sheer incomprehensible numbers. An astronomical unit, or AU, is the distance from Earth to the Sun, roughly 93 million miles, or about 150 million kilometers. That's our baseline. Pluto, at its closest approach to us, sits about 30 astronomical units away. That's almost 3 billion miles. To put that in perspective, if you could drive a car at highway speeds toward Pluto without ever stopping, it would take you over 4,000 years just to arrive. But we're not driving cars through space. We're launching spacecraft. And even our fastest machines face incredible obstacles when confronted with distances like these. The story of reaching Pluto begins with one of the most ambitious missions in the history of space exploration, NASA's New Horizons probe. On January 19, 2006, a sleek, piano-sized spacecraft lifted off from Cape Canaveral atop an Atlas V rocket. This was New Horizons, and it had one primary goal: to reach Pluto and send back the first close-up images of that distant, frozen world. From the moment it left Earth, New Horizons was breaking records. It launched at approximately 36,400 miles per hour, making it the fastest spacecraft ever launched from our planet at that time. To give you some context, that's about 10 miles every single second. Imagine blasting past entire cities in the blink of an eye. But even at that incredible velocity, New Horizons needed 9.5 years to reach Pluto. Think about that for a moment. 9.5 years of traveling at speeds we can barely comprehend, and it still wasn't a quick trip. The spacecraft zipped past the Moon's orbit in just 9 hours, something that took the Apollo astronauts 3 days. It flew by Jupiter in February 2007, using the giant planet's gravity to slingshot itself even faster toward the outer solar system. That gravity assist boosted New Horizons' speed by an additional 4 kilometers per second, a critical maneuver that shaved years off the journey. Then came the long, silent cruise through the darkness. For most of the journey, New Horizons was in hibernation mode, its systems powered down to conserve energy and reduce wear on its instruments. Mission controllers back on Earth woke it up periodically to check its health, make course corrections, and ensure everything was functioning properly. Can you imagine the tension? A billion-dollar mission coasting through the void for nearly a decade, with everything riding on a handful of moments when the spacecraft would finally wake up and do its job. And then, on July 14, 2015, history happened. New Horizons screamed past Pluto at a distance of just 7,750 miles from its surface, traveling at 32,500 miles per hour. At that moment, the spacecraft was so far from Earth that radio signals traveling at the speed of light took 4.5 hours to reach us. That means when Mission Control sent a command, they had to wait 9 hours for a response. It's like having a conversation with someone on the other side of the solar system, where every exchange takes half a day. The images New Horizons sent back were nothing short of breathtaking. We saw Pluto's heart-shaped region called Tombor Regio, vast plains of frozen nitrogen, towering mountains made of water ice, and a thin, hazy atmosphere that extended far into space. For the first time in human history, we had visited every world in our solar system that we once considered a planet. It was a triumph of engineering, patience, and human curiosity. Now, back to our story, 9.5 years to Pluto. That's nearly a decade of travel time using some of the most advanced technology we have. And here's the thing, that's just Pluto. That's still within our solar system. Proxima Centauri, the closest star beyond our Sun, is in an entirely different league of distance. We're talking about a journey that makes the trip to Pluto look like a short commute. Proxima Centauri sits approximately 4.25 light-years away from us. A light-year is the distance light travels in 1 year, moving at 670 million miles per hour, or about 300,000 kilometers per second. Nothing in the universe moves faster than light. It's the ultimate speed limit, baked into the very fabric of reality itself. So when we say Proxima Centauri is 4.25 light-years away, we're saying that even light, the fastest thing we know, takes 4 years and 3 months to make that journey. Let's put that into perspective using astronomical units, the same measurement we used for Pluto. Proxima Centauri is roughly 269,000 astronomical units from Earth. Remember, Pluto at its farthest is only about 50 AU away. We're talking about a distance that's over 5,000 times greater than the span from the Sun to Pluto. It's almost incomprehensible. So how long would it take us to get there? If we sent New Horizons toward Proxima Centauri, traveling at its cruising speed of about 36,000 miles per hour, the journey would take approximately 54,000 years. Yes, you read that right. 54,000 years. To put that in historical context, 54,000 years ago, modern humans were just beginning to migrate out of Africa. We hadn't invented writing, agriculture, or even settled into permanent communities. Entire civilizations would rise and fall in the time it would take New Horizons to reach our nearest stellar neighbor. And New Horizons, remember, was the fastest spacecraft we'd ever launched at the time. So what about our current speed record holder? That title now belongs to NASA's Parker Solar Probe, a mission designed to dive closer to the Sun than any spacecraft before it. On December 24, 2024, the Parker Solar Probe reached a staggering speed of 192.22 kilometers per second. That's roughly 430,000 miles per hour, or about 120 miles every single second. At that speed, the Parker Solar Probe could travel from New York to Los Angeles in less than 20 seconds. It's the fastest human-made object ever created, bar none. And yet, even at that mind-blowing velocity, if we pointed it toward Proxima Centauri, the journey would still take approximately 7,230 years. That's still longer than all of recorded human history. Think about what that means. With our fastest spacecraft, the one that holds the record for the highest speed ever achieved by a human-made object, we still couldn't reach even the nearest star within a single human lifetime, not even close. You could launch the mission today and your descendants 72 centuries from now would be the ones to see it arrive. That's the scale we're dealing with when we talk about interstellar travel. Now, you might be wondering, why is space travel so slow? I mean, we've been launching rockets for decades. We've sent humans to the moon, rovers to Mars, and probes to the edge of the solar system. Shouldn't we be getting faster? The answer lies in the fundamental physics of how rockets work and the brutal realities of moving through the vacuum of space. Every rocket ever built operates on the same basic principle: Newton's third law of motion. For every action, there's an equal and opposite reaction. Rockets propel themselves forward by throwing mass backward at high speed. In most cases, that mass is hot gas produced by burning chemical fuel. The space shuttle, the Saturn V that took astronauts to the moon, and even the Atlas V that launched New Horizons all relied on chemical propulsion. You ignite fuel, create an explosion in a controlled chamber, and direct that explosive force out the back of the rocket. Chemical rockets are powerful, but they have serious limitations. The biggest problem is something called the rocket equation, formulated by a Russian scientist named Konstantin Tsiolkovsky back in 1897. The rocket equation tells us that to go faster, you need more fuel. But more fuel means more weight, and more weight means you need even more fuel to lift that extra fuel. It's a vicious cycle. Eventually you hit a point of diminishing returns where adding more fuel doesn't help because you're just carrying more mass. This is why most of a rocket's weight at launch is fuel. The Saturn V rocket that sent astronauts to the moon weighed 6.2 million pounds at liftoff. Of that, roughly 5.7 million pounds was fuel. The actual payload, the stuff we cared about getting to space, was only a tiny fraction of the total mass. It's like trying to cross an ocean in a boat where 95% of the weight is the gasoline you're carrying and only 5% is the boat itself and the cargo. Chemical rockets got us to Pluto, but they're simply not fast enough for interstellar journeys. Even if we built the most efficient chemical rocket theoretically possible, we'd still be looking at travel times measured in tens of thousands of years to reach Proxima Centauri. That's because chemical reactions can only release so much energy. The speed of the exhaust gases leaving a chemical rocket tops out at around 4 to 5 kilometers per second. To go faster, we need something fundamentally different. This is where things get really interesting. Scientists and engineers have proposed dozens of alternative propulsion systems, each with its own advantages and challenges. Some of these ideas sound like pure science fiction, but they're grounded in real physics. Let me walk you through a few of them. First, there's nuclear propulsion. Instead of burning chemical fuel, you use a nuclear reactor to heat a propellant, usually hydrogen, to extremely high temperatures. The superheated gas shoots out the back of the spacecraft, providing thrust. Nuclear rockets could achieve exhaust velocities 2 to 3 times higher than chemical rockets, which means significantly faster travel speeds. NASA and other space agencies have studied nuclear thermal propulsion for decades. In fact, NASA tested nuclear rocket engines back in the 1960s and 70s. The technology works, but it's never been used for an actual space mission, partly due to political and safety concerns about launching nuclear reactors into space. Then there's ion propulsion, a technology we're actually using today on some missions. Ion engines work by electrically charging atoms of xenon gas and then accelerating them using electric fields. The ions shoot out the back of the spacecraft at speeds up to 90 kilometers per second, far faster than any chemical rocket exhaust. The catch? Ion engines produce very low thrust. They can't lift a spacecraft off the ground, but once you're in space, they can run continuously for years, gradually building up speed. NASA's Dawn mission, which explored the asteroids Vesta and Ceres, used ion propulsion. So does the European Space Agency's Bepi-Colombo mission to Mercury. If we equipped a spacecraft with ion engines and let it accelerate for years, we could potentially reach speeds that would cut the journey to Proxima Centauri down to something like 20,000 years. Still not exactly a quick trip, but it's progress. The problem is that ion engines require a lot of electrical power, which usually comes from solar panels. The farther you get from the sun, the less solar energy is available. You'd need nuclear reactors to power the engines for an interstellar mission, adding complexity and weight. Another concept that scientists find exciting is nuclear pulse propulsion, specifically a design called Project Orion. This idea is wild. Imagine a spacecraft that moves by detonating nuclear bombs behind it. Seriously. You drop a nuclear device, it explodes, and a massive shock absorber plate on the back of the spacecraft absorbs the blast, converting that explosive energy into forward motion. Studies done in the 1950s and 60s suggested that an Orion-type spacecraft could reach speeds of up to 5% the speed of light. At that velocity, you could reach Proxima Centauri in about 85 years. The challenges with nuclear pulse propulsion are enormous, though. Setting off nuclear explosions in space raises all kinds of environmental, political, and technical questions. Plus, the engineering required to build a shock absorber that could withstand repeated nuclear blasts is beyond our current capabilities. But the concept shows that with enough energy and the right technology, we could dramatically reduce travel times. Speaking of which, have you ever thought about how terrifying some places in space actually are? If you found this discussion about cosmic distances fascinating, you might want to check out my video on why the Moon is the scariest place in space. Trust me, once you learn about the extreme temperatures, the deadly radiation, and the razor-sharp lunar dust that could shred spacesuits, you'll never look at our celestial neighbor the same way again. The link is in the description and on the card above. Now let's talk about something even more ambitious: light sails. This concept takes advantage of the fact that light carries momentum. When photons from the sun or from a powerful laser hit a reflective surface, they exert a tiny amount of pressure. It's incredibly small, but in the vacuum of space, even tiny forces can add up over time. A light sail is essentially a giant, ultra-thin mirror attached to a spacecraft. As light hits the sail, it pushes the craft forward. The Planetary Society has already demonstrated this technology with their light sail missions, small satellites that successfully used sunlight for propulsion. But for interstellar travel, we'd need something much more powerful. Enter the breakthrough Starshot initiative, announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner. Their plan is to build thousands of tiny spacecraft, each weighing only a few grams, equipped with light sails. These miniature probes would be accelerated by an enormous array of ground-based lasers, potentially reaching speeds of 20% the speed of light. At 20% light speed, a Starshot probe could reach Proxima Centauri in just 20 years. That's within a human lifetime. The probe would zip past the star system, snap photos, gather data, and beam the information back to Earth. The catch: the technology doesn't exist yet. We'd need to develop incredibly powerful laser arrays, build sails that can withstand the intense heat without vaporizing, and miniaturize all the scientific instruments to fit on a spacecraft the size of a postage stamp. It's ambitious, maybe even audacious, but it's not impossible. Here's something that really puts all of this into perspective. The Voyager 1 probe, launched in 1977, is currently the most distant human-made object from Earth. It's now over 15 billion miles away, far beyond Pluto, traveling through interstellar space. Voyager 1 is moving at about 38,000 miles per hour relative to the Sun. At that speed, if it were headed toward Proxima Centauri, which it's not, it would take roughly 77,000 years to get there. 77,000 years. That spacecraft has been traveling for nearly 50 years and has barely left our cosmic neighborhood. This really hammers home the scale of the challenge. Interstellar space is vast beyond human comprehension. The distances involved are so enormous that our usual ways of thinking about travel completely break down. When we talk about flying to another country, we measure the trip in hours. When we talk about space missions to Mars or Pluto, we measure in months or years. But when we talk about reaching another star, we have to start thinking in terms of centuries or millennia unless we develop radically new technologies. And yet, despite these incredible obstacles, humanity keeps pushing forward. We keep asking questions, designing new missions, and dreaming bigger dreams, because that's what we do. We're explorers by nature. We look at the impossible and ask, how can we make it possible? Let's step back for a moment and really appreciate what we're dealing with here. When we look up at the night sky, our brains aren't wired to comprehend the distances we're seeing. That twinkling point of light you see, it might be a star 4 light years away, or it might be a galaxy millions of light years distant. Our ancestors looked at the same sky and imagined the stars were just holes poked in a celestial dome, letting heavenly light shine through. They had no idea they were looking at suns like ours, separated by gulfs of emptiness so vast that even light, the fastest thing in existence, takes years to cross them. Here's an analogy that might help. Imagine you could shrink the entire solar system down to the size of a city. In this model, the Sun would be about the size of a beach ball sitting in the center of town. Earth would be a tiny marble orbiting about 100 feet away. Pluto, at its farthest point, would be roughly half a mile from the Sun. Now, where would Proxima Centauri be in this scale model? It would be sitting approximately 13,000 miles away. That's roughly the distance from New York City to Sydney, Australia. That's the gap between our solar system and the very nearest star. When you think about it that way, the challenge becomes crystal clear. We've managed to send a spacecraft half a mile down the street to visit Pluto. Now we're talking about sending one to Sydney, except we can't use airplanes, cars, or any conventional transportation. We're stuck using the equivalent of walking, and the journey takes thousands of years. But let's dig deeper into why Pluto itself was such a monumental achievement. When New Horizons launched, Pluto was still officially classified as the 9th planet. Just 7 months after launch, the International Astronomical Union reclassified it as a dwarf planet, sparking debates that continue to this day. Regardless of what we call it, reaching Pluto represented the completion of a 50-year quest to visit all the major worlds in our solar system. The journey wasn't just about distance, it was about precision. Imagine trying to hit a target the size of a small town from nearly 3 billion miles away, while both you and the target are moving at tens of thousands of miles per hour. The navigation required for New Horizons was astounding. Mission controllers had to account for the gravitational pull of the Sun, all the planets, even some of the larger asteroids. They had to predict where Pluto would be 9.5 years in the future and aim for that point in space. During the approach, the team made several course corrections, tiny adjustments to New Horizons' trajectory. One of the final maneuvers, performed just 2 weeks before the flyby, lasted only 23 seconds. It changed the spacecraft's velocity by a mere 27 centimeters per second, about half a mile per hour. But without that adjustment, New Horizons would have arrived 20 seconds late and 114 miles off target. At the speeds involved, 20 seconds and 100 miles could mean the difference between success and failure, between capturing those historic images and missing Pluto entirely. Think about the patience required. Engineers worked on this mission for years before launch. Then they had to wait almost a decade for the payoff. And the actual flyby? It lasted only a few hours. New Horizons was moving so fast that it couldn't slow down or go into orbit around Pluto. It had one chance to get everything right. All those years of planning, building, launching, and waiting came down to a single pass. And the spacecraft delivered. The images revealed a world far more geologically active and complex than anyone expected. Scientists found evidence of recent surface changes, meaning Pluto isn't just a dead, frozen rock. Something is happening there, even now. We saw nitrogen glaciers flowing across plains, mountain ranges as tall as the Rockies made of solid water ice, and a reddish polar cap composed of methane and nitrogen ices. Pluto has weather, seasons, and possibly even a subsurface ocean of liquid water hidden beneath its frozen crust. Here's what really gets me. Everything we knew about Pluto before New Horizons could fit on a single page. Our best telescopes could barely resolve it as more than a fuzzy blob. We knew it had moons. We knew its approximate size and density, that was about it. In just a few hours of close observation, New Horizons revolutionized our understanding. We went from ignorance to insight in the blink of an eye, cosmically speaking. This is the power of exploration. This is why we go. Not because it's easy, but because it's hard. Because every new world we visit expands our understanding of how planets form, evolve, and change over billions of years. Pluto taught us that even in the frozen outer reaches of the solar system, far from the sun's warmth, worlds can be dynamic and fascinating. Now imagine applying that same spirit of exploration to Proxima Centauri. What would we find there? We already know the star has at least 2 confirmed planets. Proxima Centauri b, discovered in 2016, orbits in the star's habitable zone, the region where temperatures might allow liquid water to exist on a planet's surface. It's roughly Earth-sized with a mass about 1.3 times that of our planet. It completes an orbit every 11.2 days because it's so close to its star, only about 5% of the distance between Earth and the Sun. But here's the catch. Proxima Centauri is a red dwarf, much smaller and cooler than our Sun. Red dwarfs are known for being temperamental. They produce powerful stellar flares, sudden bursts of radiation, and charged particles that can strip away a planet's atmosphere over time. Proxima Centauri b is so close to its star that it's likely tidally locked, meaning one side always faces the star while the other is in eternal darkness. One hemisphere would be scorched, the other frozen. If there's life there, it would have to survive in a narrow twilight band between eternal day and endless night, or perhaps in subsurface oceans protected from the radiation above. We don't know if Proxima Centauri b has an atmosphere. We don't know if it has water. We don't know if it's a rocky world like Earth or something entirely different. The only way to truly answer these questions is to go there and look. Telescopes can tell us some things, but they have limits. To really understand an alien world, you need to visit it, study it up close, maybe even land on it. And that brings us back to the central problem, time. Even if we launch the fastest spacecraft we've ever built toward Proxima Centauri today, the people who designed and built it would be long dead before it arrived. Their children would be dead. Their grandchildren would be dead. In fact, depending on the technology used, dozens or even hundreds of generations might pass before the spacecraft reached its destination. This raises profound questions. How do you maintain a mission across centuries? Who pays for it? Who monitors it? What if technology advances during the journey and we build faster ships that overtake the original probe? What if humanity loses interest or faces crises that divert resources away from space exploration? These aren't just technical challenges. They're social, political, and philosophical ones. Some scientists have proposed building generation ships, enormous spacecraft designed to support entire communities for the duration of an interstellar voyage. The people who launch wouldn't be the ones to arrive. Instead, their descendants, born and raised in space, would be the ones to finally reach the destination. It's a romantic idea, but the practical challenges are staggering. You'd need to create a completely self-sustaining ecosystem, recycle everything perfectly, maintain social stability across generations, and ensure the ship's technology doesn't fail over centuries of operation. Others suggest we might put astronauts into suspended animation, slowing their metabolism to a crawl so they age much more slowly during the journey. This is pure science fiction right now. We have no idea how to safely place humans in stasis for years, let alone decades or centuries. Medical science hasn't solved the basic problems of freezing and thawing human tissue without causing massive cellular damage, much less keeping someone in a state between life and death for generations. There's another approach that's perhaps more realistic. In the near term, sending robotic probes. Machines don't need food, water, or air. They don't get bored or lonely. They can be powered down during the long cruise and reactivated when they reach their destination. The Breakthrough Starshot project embraces this philosophy. Send thousands of tiny, lightweight probes accelerated by lasers, Some will fail, but some will succeed. The successful ones will beam back data and images, giving us our first real look at another star system. But even if we succeed in sending probes to Proxima Centauri, there's still the communication delay to consider. Remember, it takes light 4.25 years to travel from Proxima Centauri to Earth. That means when a probe arrives and starts sending data, we won't receive it until more than 4 years later. And if we want to send new instructions based on what the probe discovers, those commands will take another 4 years to arrive. It's like having a conversation with a delay of 8.5 years between question and answer. Imagine the scenario. A probe reaches Proxima Centauri and starts taking pictures of Proxima Centauri b. Scientists on Earth, 4.25 years later, finally see the images. They notice something unusual, maybe evidence of an atmosphere or strange surface features. They want the probe to investigate further, so they send new commands. Those commands arrive at the probe 4.25 years after being sent. By the time the probe responds, nearly a decade has passed since the initial discovery. This is the reality of interstellar exploration. Everything happens in slow motion from our perspective. There are no quick decisions, no real-time adjustments. You program the mission as best you can before launch, then trust that your probe is smart enough to handle whatever it encounters. Let's talk about something that often gets overlooked in discussions about space travel: energy. We've talked about propulsion systems and spacecraft design, but at the heart of everything is a simple question: where does the energy come from? Moving a spacecraft, even a small one, to a significant fraction of the speed of light requires absolutely staggering amounts of energy. We're talking about amounts that dwarf anything humanity currently produces. To put this in perspective, let's do some math. Don't worry, I'll keep it simple. The kinetic energy of a moving object depends on its mass and velocity. The formula is 1/2 times mass times velocity squared. That velocity squared part is crucial. It means that doubling your speed requires 4 times as much energy. Tripling your speed needs 9 times the energy. This relationship gets brutal very quickly when you're talking about spacecraft moving at significant fractions of light speed. Let's say we want to send a small probe, maybe weighing about a ton, to Proxima Centauri at 10% the speed of light. That's already a conservative estimate, much slower than the 20% speed proposed by breakthrough Starshot. At 10% light speed, the journey would take about 42 years. How much energy would we need to accelerate that probe to that speed? The answer is roughly 450,000 terajoules. To give you a sense of scale, that's equivalent to the total energy output of about 10,000 nuclear power plants running for an entire day. It's approximately the total energy consumption of the entire United States for about 4 days. And that's just to accelerate the probe. We're not even talking about the energy needed to run its instruments, maintain communication, or decelerate when it arrives. Where would this energy come from? Solar panels won't work once you're far from the sun. Batteries heavy enough to store that much energy would weigh far more than the spacecraft itself, defeating the purpose. Chemical fuel can't provide those energy densities. This is why concepts like laser propulsion or nuclear pulse propulsion become attractive. They externalize the energy source. The laser array stays on Earth or in orbit around the Sun, beaming energy to the spacecraft's light sail. The nuclear bombs in a pulse propulsion system carry their own energy in a highly concentrated form. But even these solutions face enormous challenges. The laser array for breakthrough Starshot would need to produce about 100 gigawatts of power, roughly equivalent to the electrical output of 100 large power plants. And that power would need to be focused with incredible precision onto a sail measuring just a few meters across from a distance of millions of kilometers. The engineering required is at the very edge of what might be possible with future technology. There's another fundamental problem we haven't discussed yet: the interstellar medium. Space isn't perfectly empty. Even in the vast gulfs between stars, there are stray atoms and molecules, mostly hydrogen, floating around. The density is incredibly low, only about 1 atom per cubic centimeter on average. For comparison, the air you're breathing right now contains about 25 billion molecules per cubic centimeter. Interstellar space is a vacuum better than anything we can create in a laboratory on Earth. But when you're moving at 10 or 20% the speed of light, even that incredibly thin gas becomes a problem. Each atom you hit transfers momentum, creating drag that slows you down. Worse, at those velocities, collisions with atoms become dangerous. A hydrogen atom hitting your spacecraft at 20% light speed carries as much kinetic energy as a rifle bullet. Over the course of a journey lasting decades, your spacecraft would be sandblasted by trillions of these microscopic impacts. This means any interstellar spacecraft needs shielding, something to absorb or deflect these particle impacts. But shielding adds mass, and more mass requires more energy to accelerate. Once again, we run into the tyranny of the rocket equation. Every kilogram of shielding you add means more energy needed for propulsion, which might require a bigger laser array or more nuclear bombs, or a larger light sail, which adds more mass, which requires more energy. It's a vicious cycle. Some scientists have proposed using magnetic fields to deflect charged particles, similar to how Earth's magnetic field protects us from solar wind. A spacecraft could generate a powerful magnetic field that pushes ions away before they strike the hull. This is elegant in theory, but creating a magnetic field strong enough to provide meaningful protection would require either superconducting magnets or enormous amounts of electrical power. And of course, magnetic fields only work on charged particles. Neutral atoms would sail right through. Another challenge: cosmic rays. These are high-energy particles, mostly protons, that zip through space at nearly the speed of light. They originate from supernovae, pulsars, black holes, and other violent cosmic events. When a cosmic ray hits matter, it can create cascades of secondary particles and radiation. For astronauts on a long journey, cosmic ray exposure is a serious health risk, potentially causing cancer, cataracts, and damage to the central nervous system. Earth's atmosphere and magnetic field shield us from most cosmic rays. On the International Space Station, astronauts receive about 150 times more radiation exposure than they would on Earth's surface. On a journey to Mars, lasting 6 to 9 months, astronauts would receive even more. But on an interstellar voyage lasting years or decades, the cumulative radiation dose would be enormous. Any crewed mission would need heavy shielding, again adding mass and complexity. This is one reason why most serious proposals for interstellar exploration focus on robotic probes rather than human missions. Robots don't care about radiation, they don't need food, water, or psychological support. They can be miniaturized and mass-produced. If one fails, it's disappointing but not tragic. You can't say the same about human explorers. Yet there's something deeply human about the desire to go ourselves, to set foot on alien soil, to see distant worlds with our own eyes rather than through the sensors of a machine. This tension between the practical advantages of robotic exploration and the emotional appeal of human presence is at the heart of many debates about the future of space exploration. Let me share something that really illustrates the timescales we're dealing with. The Voyager probes, launched in 1977, are still operational today, almost 50 years later. They're the longest-running space mission in history. Their plutonium power sources are gradually decaying, producing less and less electricity each year. Scientists estimate that by the mid-2020s to early 2030s, the Voyagers won't have enough power to run any of their instruments. They'll go silent, becoming derelict spacecraft coasting through interstellar space forever. But here's the thing, even after they go silent, the Voyagers will continue their journey. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. That's relatively close, cosmically speaking. But the spacecraft will have been dead for almost 40,000 years by then. If anyone or anything finds it, they'll be examining an ancient relic, a message in a bottle from a civilization that may or may not still exist. Both Voyager probes carry a golden record, a 12-inch gold-plated phonograph record containing sounds and images from Earth. It includes greetings in 55 languages, music from various cultures, natural sounds like thunder and bird songs, and encoded images showing what humans look like, where we live, and what our world is like. The record is accompanied by a stylus and instructions for playing it, etched in symbolic language that we hope any technologically advanced civilization could decipher. It's a poetic gesture, a way of saying, "We were here. This is who we are." But it also underscores the profound loneliness of space. The Voyagers will drift for tens of thousands of years before coming anywhere near another star. The odds of them actually being found by an alien civilization are astronomically small. Space is just too vast and the Voyagers are just too tiny. This brings us to an important realization. When we talk about exploring other star systems, we're not just talking about overcoming technical challenges. We're talking about accepting a fundamentally different relationship with time. On Earth, we're used to instant gratification, or at least results within our lifetime. We start a project and expect to see it finished. We ask questions and want answers. Interstellar exploration doesn't work that way. The people who design and launch an interstellar mission will never see it succeed. They're doing it for future generations, for people not yet born who will receive the data and images decades or centuries later. It requires a kind of long-term thinking that doesn't come naturally to our species. We evolved to think in terms of days, seasons, and years, not centuries or millennia. Yet we've done it before. Medieval stonemasons worked on cathedrals that took 100 years or more to complete. They knew they'd never see the finished building, but they worked on it anyway, trusting that future generations would continue the effort. Ancient civilizations planted olive groves knowing that the trees wouldn't bear significant fruit for decades, long after the planters had died. In a way, interstellar exploration is the ultimate cathedral, the ultimate olive grove. We start the work knowing we'll never see the result, but we do it because it matters. And it does matter. Understanding our place in the universe, knowing whether we're alone or whether life exists elsewhere, exploring the incredible diversity of planets and stars and galaxies, these questions speak to something fundamental in human nature. We are curious creatures. We ask questions. We explore. It's what we've always done, from our ancestors who walked out of Africa to the astronauts who traveled to the moon. Proxima Centauri represents the next frontier, a destination that will test the limits of our technology, our patience, and our commitment to knowledge. It's a star with planets, worlds that might harbor conditions suitable for life, or at least for understanding how planetary systems form and evolve. Every star system we can study adds to our understanding of how common or rare Earth-like worlds might be. Now let's talk about something that might surprise you. We're actually getting better at finding planets around other stars. When I was growing up, we didn't know of a single planet beyond our solar system. The first confirmed exoplanet orbiting a Sun-like star wasn't discovered until 1995. That's less than 30 years ago. Today, we've confirmed over 5,000 exoplanets, and we're discovering new ones almost every week. This explosion of discovery has been driven by increasingly sophisticated telescopes and detection methods. The Kepler Space Telescope, launched in 2009, revolutionized the field by staring at a single patch of sky and watching for tiny dips in starlight caused when planets pass in front of their stars. This technique, called the transit method, allowed Kepler to discover thousands of planets. The James Webb Space Telescope, which began operations in 2022, can actually analyze the atmospheres of some exoplanets, detecting the chemical signatures of gases that might indicate biological activity. We now know that planets are common. Nearly every star has at least one planet, and many have multiple worlds orbiting them. Rocky planets roughly the size of Earth appear to be especially abundant. We've found planets orbiting in the habitable zones of their stars where temperatures might allow liquid water to exist. We've found super-Earths, mini-Neptunes, hot Jupiters, frozen ice worlds, and bizarre planets unlike anything in our solar system. But here's the frustrating part. Even with our best telescopes, planets around other stars are incredibly difficult to observe. Proxima Centauri b, the closest known exoplanet to Earth, has never been directly imaged. We know it exists because of the subtle wobble it causes in its star's motion and the tiny dimming when it passes in front of the star. But we can't take a picture of it, it's just too small and too close to its bright star from our perspective. Imagine trying to spot a firefly hovering next to a searchlight from 100 miles away. That's essentially what we're trying to do when we look for planets around other stars. The star is billions of times brighter than the planet, and the planet is so close to the star from our viewpoint that the glare overwhelms any light reflected from the planet's surface. This is why actually going to Proxima Centauri would be so valuable. A probe in that star system could take detailed images of Proxima Centauri b, study its atmosphere if it has one, measure its magnetic field, analyze its surface composition, and search for any signs of life. All the things we take for granted when studying planets in our own solar system become possible. But first we have to get there. Let's return to the numbers for a moment because they really drive home the challenge. Pluto is approximately 30 to 50 astronomical units from Earth, depending on where both worlds are in their orbits. The journey took 9.5 years. Proxima Centauri is 269,000 astronomical units away. If we scale that linearly, keeping everything else the same, the journey would take about 51,000 years, and that's using the same spacecraft that holds the record for the fastest launch speed from Earth at the time. The Voyager probes are traveling at roughly 3.2 to 3.5 astronomical units per year. At that rate, they'd take 77,000 to 84,000 years to reach the distance of Proxima Centauri. The Parker Solar Probe, our current speed champion at 430,000 miles per hour, would still need over 7,000 years. These numbers are so large they'd lose meaning after a while. 7,000 years ago, humans had just invented the wheel. Writing wouldn't be invented for another 2,000 years. The pyramids of Egypt were still 3,000 years in the future. Trying to imagine a project that spans that much time is almost impossible. But let's try. Let's imagine that ancient Sumerians living 7,000 years ago somehow launched a spacecraft toward Proxima Centauri. They used their most advanced technology, whatever that might have been. That spacecraft would just now be arriving. Think about everything that's happened in human history during that time. Empires rose and fell, languages evolved and died, entire civilizations flourished and vanished. And through it all, that hypothetical spacecraft was silently crossing the void, headed for a destination chosen by people whose names and cultures have been forgotten for millennia. This thought experiment reveals something profound. Interstellar travel, at least with current or near-future technology, isn't just a technical challenge, it's a challenge to our entire way of thinking about projects, missions, and goals. We need to develop a cosmic perspective, a way of thinking that embraces timescales far beyond individual human lives. Some philosophers and scientists argue that this is actually one of the most valuable aspects of space exploration. It forces us to think long-term, to consider the future of our species not in terms of election cycles or quarterly earnings reports, but in terms of centuries and millennia. It makes us ask, What kind of civilization do we want to be? What legacy do we want to leave? Are we willing to start projects that our distant descendants will complete? These aren't just abstract philosophical questions, they have practical implications. Climate change, for example, operates on timescales of decades to centuries. The decisions we make today will affect people living 100 years from now. Managing nuclear waste requires thinking thousands of years ahead, since some radioactive materials remain dangerous for 10,000 years or more. Building a sustainable relationship with our planet's ecosystems means thinking in terms of generations, not just years. Space exploration, particularly interstellar exploration, is the ultimate exercise in long-term thinking. It forces us to grapple with questions about who we are and what we value, and maybe that's part of its value, even if we never actually send a probe to Proxima Centauri. The act of seriously contemplating such a journey changes how we think about ourselves and our place in the cosmos. Now let's consider a different angle. What if we're thinking about this all wrong? What if instead of trying to send humans or even robots to other star systems, we should focus on sending information? After all, what we really want is knowledge about those distant worlds. We want to know what they're like, whether they harbor life, what we can learn from studying them. Do we actually need to send physical objects, or could we accomplish the same goals in other ways? One idea that's been proposed is to use advanced artificial intelligence. Imagine sending a tiny probe equipped with a highly sophisticated AI system. The probe wouldn't need to carry elaborate scientific instruments or communication arrays. Instead, it would carry the instructions for building them. Upon arrival at Proxima Centauri, the probe would land on an asteroid or moon, mine raw materials, and use those materials to construct a much larger facility. This facility would then conduct the actual scientific observations and beam the results back to Earth. This concept, sometimes called a self-replicating probe or von Neumann probe, after mathematician John von Neumann, could in theory explore the entire galaxy. Each probe reaches a star system, builds copies of itself, and sends those copies to other nearby stars. Exponential growth means that even with relatively slow travel speeds, the probes could visit every star in the galaxy within a few million years. Of course, this raises all sorts of questions and concerns. What if the probes malfunction and start replicating uncontrollably? What if they run out of control and consume all available resources like a cosmic version of grey goo? What if another civilization has already launched such probes and they arrive in our solar system? These are the kinds of scenarios science fiction writers love to explore, but they're also serious considerations for scientists thinking about the long-term future of space exploration. There's another approach that doesn't require sending anything physical at all: interstellar communication. Instead of going to Proxima Centauri, we could try to talk to anyone who might be living there. Radio waves travel at the speed of light, so a message would take 4.25 years to reach Proxima Centauri and another 4.25 years for a response to come back. That's a long conversation, but it's much faster than sending a spacecraft. The problem, of course, is that we have no idea if anyone is listening. We've been beaming radio and television signals into space for about a century now. Those signals form an expanding bubble around Earth, currently about 100 light-years in radius. Any civilization within that bubble with sufficiently sensitive radio telescopes could, in theory, detect our presence. But the signals get weaker as they spread out, eventually becoming indistinguishable from background noise. We've also conducted deliberate attempts to communicate with potential extraterrestrial civilizations. The most famous is probably the Arecibo message, a brief radio transmission sent toward the globular cluster Messier 13 in 1974. That message will take 25,000 years to reach its destination, and if anyone there responds, we won't hear back for another 25,000 years. It was more symbolic than practical, a way of demonstrating that we could send a message if we wanted to. The search for extraterrestrial intelligence, known as SETI, has been listening for signals from other civilizations for decades. Researchers use radio telescopes to scan the sky, looking for patterns that might indicate an artificial transmission rather than natural cosmic noise. So far, they've found nothing conclusive. The famous WOW signal detected in 1977 was a strong, narrowband radio signal that lasted 72 seconds and appeared to come from the direction of the constellation Sagittarius. It's never been detected again, and we still don't know what caused it. The silence is puzzling. If intelligent life is common in the universe, why haven't we heard from anyone? This question, known as the Fermi paradox after physicist Enrico Fermi, has spawned dozens of possible explanations. Maybe intelligent life is extremely rare. Maybe civilizations tend to destroy themselves before they develop interstellar communication. Maybe they're out there but deliberately staying quiet. Maybe they're communicating using methods we haven't thought of yet. Maybe they exist on timescales so different from ours that we're like mayflies trying to have a conversation with trees. Or maybe, and this is a sobering thought, space is simply too vast. Even if the galaxy is teeming with civilizations, the distances between stars might be too great for meaningful communication or travel. We might be like villages scattered across a vast ocean, each unaware of the others, each thinking they're alone. This brings us to one of the most profound questions in all of science. Are we alone? It's a question that has haunted humanity for as long as we've looked up at the stars. Every culture, every civilization has asked it in one form or another. And for the first time in human history, we might actually be able to answer it within the next few decades. The discovery of thousands of exoplanets has fundamentally changed this conversation. We now know that the raw materials for life, the basic building blocks, are abundant throughout the universe. Carbon, hydrogen, oxygen, nitrogen, the elements that make up living things, are among the most common elements in the cosmos. Water, essential for life as we know it, appears to be everywhere. We've found it on Mars, on the moons of Jupiter and Saturn, in comets, even in clouds of gas between stars. The conditions necessary for life also seem to be relatively common. Many stars have planets in their habitable zones. Organic molecules, the complex carbon-based compounds that are the precursors to life, form naturally in space. We've detected amino acids, the building blocks of proteins, in meteorites. We've found sugars in interstellar gas clouds. The universe appears to be a chemistry lab constantly cooking up the ingredients for life. But there's a huge difference between having the right ingredients and actually having life. We still don't fully understand how life began on Earth. We know it happened relatively quickly, geologically speaking. Earth formed about 4.5 billion years ago. The earliest evidence for life dates back to around 3.8 billion years ago, possibly even earlier. That means life emerged within the first few 100 million years after our planet cooled enough to have liquid water on its surface. Does that mean life arises easily whenever conditions are right? Or did Earth get incredibly lucky? We simply don't know. We have a sample size of 1. Earth. Everything we know about biology, evolution, and the origin of life comes from studying organisms that all share a common ancestor. We have no idea if life elsewhere would be similar to Earth life or completely different. This is why finding even simple life on Mars or Europa or Enceladus would be so revolutionary. It would tell us that life can arise independently in different environments. It would suggest that life might be common throughout the universe. On the other hand, if we explore our solar system thoroughly and find nothing but barren rocks and frozen wastes, that would also tell us something important. It might suggest that life is rare, that Earth is special, that we shouldn't expect to find living worlds around every star. Proxima Centauri b sits right at the heart of this question. It's in the habitable zone of its star, which means temperatures might be right for liquid water. But as we discussed earlier, it faces challenges. The star produces powerful flares. The planet is probably tidally locked. It might not have an atmosphere. Or it might have a thick atmosphere that creates a runaway greenhouse effect, making the surface hotter than Venus. We won't know until we get there and look. Imagine if a probe reached Proxima Centauri b and found clear evidence of life. Maybe it detected oxygen and methane in the atmosphere, a combination that on Earth is produced by living organisms. Maybe it photographed green continents, suggesting photosynthetic life. Maybe it even picked up radio signals or other signs of technology. The implications would be staggering. First, it would answer one of humanity's oldest questions: we are not alone. Life exists elsewhere in the universe. Second, it would tell us that life can thrive around red dwarf stars, which are the most common type of star in the galaxy. If life can exist on planets around red dwarfs, then potentially habitable worlds are even more abundant than we thought. Third, it would raise new questions. How did life arise there? Is it similar to Earth life, suggesting a common origin or universal principles? Or is it completely different, showing that life can take forms we never imagined? Now consider the opposite scenario. Our probe reaches Proxima Centauri b and finds a sterile world. No atmosphere, or an atmosphere devoid of any chemical signatures suggesting life. No liquid water, no organic molecules, just rocks and radiation. What would that tell us? It might suggest that even planets in habitable zones often fail to develop life. It might mean life is even rarer than we feared. Or it might simply mean that this particular world didn't win the cosmic lottery. After all, we'd only have examined one planet around one star. That's still a tiny sample size. This uncertainty is part of what makes exploration so compelling. We genuinely don't know what we'll find. Every mission to a new world has surprised us. Mars turned out to have once had rivers and lakes. Venus has bizarre atmospheric chemistry that we still don't fully understand. Jupiter's moon, Europa, almost certainly has a global ocean beneath its icy crust. Saturn's moon, Titan, has lakes and rivers of liquid methane, weather systems, and complex organic chemistry. We've been surprised again and again. What might we find around Proxima Centauri? Maybe Proxima b is a water world, completely covered by a global ocean hundreds of kilometers deep. Maybe it's a desert planet with a thin atmosphere and extreme temperature swings. Maybe it has ice sheets on its dark side and boiling seas on its star-facing hemisphere, with a narrow temperate band in between where bizarre life forms have adapted to eternal twilight. Or maybe it's something we can't even imagine yet, a type of world we've never encountered. The frustrating thing is that we're so close, cosmically speaking, and yet so impossibly far. 4.25 light-years might as well be 4 million light-years given our current technology. It's like being able to see a treasure chest on an island across the ocean, but having no boat to reach it. We know it's there, we can observe it from a distance, but we can't touch it, can't study it up close, can't truly understand it. This is why scientists are so eager to develop faster propulsion systems. Every percentage point increase in velocity translates to years or decades shaved off the journey time. If we could reach 10% light speed, the trip drops to about 42 years. At 20%, it's 21 years. At 50%, which is probably close to the limit for any realistic propulsion system, we're looking at 8.5 years. Still a long journey, but one that could be accomplished within a human career. But reaching even 10% light speed is extraordinarily difficult. Remember those energy requirements we discussed? they scale with the square of velocity. Going from 1% to 10% light speed doesn't require 10 times as much energy, it requires 100 times as much. The engineering challenges multiply accordingly. There's also the problem of deceleration. Most propulsion concepts, like light sails pushed by lasers, are great at accelerating a spacecraft to high speeds. But how do you slow down when you get there? If you just cruise past at 20% light speed, you only have a brief window to collect data, just like New Horizons at Pluto. To truly explore a system, you want to go into orbit, and that requires killing your velocity. Some proposals suggest using the destination star's light for deceleration. The spacecraft could deploy a different type of sail that creates drag against the star's radiation, gradually slowing down. Others propose sending a second laser array ahead of the main mission, positioning it to fire back and decelerate the spacecraft. These ideas are clever but add enormous complexity and cost. Another option is the mission profile used by New Horizons. Just accept that you'll be doing a fast flyby. Design the probe to collect as much data as possible during a brief encounter, then transmit everything back home. It's not ideal, but it's simpler and more achievable with near-term technology. The breakthrough Starshot concept embraces this approach. The tiny probes would zip through the Proxima Centauri system at 20% light speed, snap pictures and take measurements for a few hours, then continue on into deep space while beaming the data back to Earth. Let me share something that really puts this in perspective. The New Horizons flyby of Pluto collected about 50 gigabits of data during the encounter. Because the spacecraft was so far away and had a relatively weak transmitter, it took 16 months to send all that data back to Earth. 16 months to transmit 50 gigabits from the edge of our solar system. Now imagine trying to transmit data from Proxima Centauri, which is about 9,000 times farther away. The signal strength would be weaker by a factor of 81 million. To transmit the same amount of data in a reasonable time frame, you'd need a transmitter 81 million times more powerful, or a receiving antenna on Earth 81 million times larger, or some combination of the two. The engineering challenges are immense. This is where miniaturization becomes crucial. If you can pack all your instruments into a probe the size of a microchip, you need less power to transmit because you're sending less data. If the probe only needs to send back a few high-resolution images and some basic measurements rather than gigabits of detailed scientific data, the communication problem becomes more manageable. It's a trade-off between capability and feasibility. The Breakthrough Starshot team has calculated that their tiny probes could transmit data back to Earth at about a kilobit per second using a small onboard laser. At that rate, sending a single high-resolution image would take hours. But it would work, and that's what matters. A single image of Proxima Centauri b, taken from close range, would be worth the decades-long wait. Think about what that image would represent. It would be the first photograph of a planet orbiting another star, taken up close. It would be proof that we can reach beyond our solar system. It would be humanity's first real step toward becoming an interstellar species. The image might show clouds, continents, oceans, or alien landscapes beyond our imagination, or it might show a barren, cratered ball of rock. Either way, it would be transformational. This is the power of exploration. Every new discovery, every new image, every answer we find generates 10 new questions. We thought Pluto would be a dead, boring ice ball. Instead, it turned out to be geologically active and fascinatingly complex. We thought Mars was dry and lifeless. Instead, we found evidence of ancient rivers and lakes and tantalizing hints that liquid water might still flow seasonally. We keep being surprised because the universe is more interesting, more diverse, and more wonderful than we ever imagined. Let's shift gears for a moment and talk about what happens after we send a probe to Proxima Centauri. Let's say we succeed. We launch a mission, whether it's a tiny Starshot probe or something larger and more sophisticated. It accelerates to a significant fraction of light speed and begins its decades-long journey across the interstellar void. What happens back on Earth during that time? This is where things get philosophically interesting. The probe is on its way, but the people who built it are aging, retiring, dying. New generations of scientists come along who didn't work on the original mission. They've inherited it, like a family heirloom or a historical monument. They have to maintain the infrastructure needed to receive signals from the probe. They have to keep the receivers operational, the data processing systems updated, the knowledge of how the mission works alive. Over decades, technology will advance dramatically. When the Voyager probes launched in 1977, personal computers barely existed. The internet as we know it hadn't been invented. Cell phones were science fiction. The computers on board the Voyagers had less processing power than a modern electronic greeting card, yet they've functioned for almost 50 years because they were built well and because NASA has maintained the infrastructure to communicate with them. Now imagine maintaining that infrastructure not for 50 years, but for 100 or 200 or more. Entire generations of engineers and scientists would dedicate their careers to supporting a mission that launched before they were born and will reach its destination after they die. It requires a kind of institutional commitment that's rare in human society. But here's something encouraging. We've actually done this before, at least on smaller timescales. The Hubble Space Telescope was deployed in 1990 and is still operational today, more than 30 years later. Multiple generations of astronauts have serviced it, updating its instruments and repairing systems. Scientists who analyzed Hubble data in the 1990s are now retired, and new scientists who weren't even born when Hubble launched are using it for their research. The mission has been passed down like a sacred trust. The same thing happens with ground-based observatories. Some telescopes operate for 50 years or more, with maintenance crews and astronomers coming and going over the decades. The institution persists even as individuals pass through. An interstellar mission would require this same kind of long-term institutional stability, just on an even grander scale. There's another factor to consider. What if we invent faster propulsion technology while the first probe is still en route? This is sometimes called the weight equation problem. If technology continues to improve, there might always be an incentive to wait a bit longer before launching, because the next generation of spacecraft will be faster and better. But if you keep waiting, you never launch anything. Imagine we send a probe in 2030 using the best technology available, and it will take 100 years to reach Proxima Centauri. But then in 2050, we develop better technology that could make the trip in 50 years. Do we launch a second probe that will overtake the first? What about the resources invested in the first mission? And what happens in 2070 when even better technology emerges? This paradox has troubled mission planners for decades. The solution, generally speaking, is to launch when you have reliable technology that can achieve your goals, even if better technology might be on the horizon. Otherwise, you'll wait forever and nothing will ever be accomplished. The first interstellar probe might be overtaken by later missions, but it will still be the first. It will still make history, and the data it collects, even if it arrives after data from faster probes, will still be valuable for comparison and verification. There's a beautiful parallel here with the history of Antarctic exploration. Early explorers reached the South Pole using dog sleds and raw human endurance. It took months of grueling travel through some of the harshest conditions on Earth. Today, you can fly to the South Pole in a few hours, but we don't dismiss those early expeditions as pointless just because later explorers had better technology. The first expeditions opened the way, proved it could be done, and laid the groundwork for everything that followed. The first mission to another star system will be the same. It will be crude by the standards of future technology. It might be overtaken by later, faster probes. But it will be the one that proved interstellar travel is possible, that showed humanity can reach beyond our solar system. That achievement can never be taken away. Now let's talk about something that often gets overlooked. The sheer beauty and grandeur of what we're discussing. We're talking about sending human-made objects to another star. Think about that. For all of human history, the stars were unreachable, literally untouchable. They were points of light in the sky, useful for navigation, inspiring for poetry, but fundamentally beyond our reach. Then, in the span of a single human lifetime, we went from the first powered airplane flight to landing people on the moon. We went from wondering if planets existed around other stars to cataloguing thousands of them. We went from thinking Earth might be the only inhabited world in the universe to seriously discussing how to search for life on exoplanets. The pace of progress has been breathtaking, and now we're on the cusp of the next great leap, reaching another star. It won't be easy, it won't be quick, but it's starting to feel achievable. For the first time in history, we have serious, scientifically grounded proposals for interstellar missions. We have organizations like Breakthrough Starshot actively developing the technology. We have NASA and other space agencies studying the problem. We're making progress. What drives this? Why do we care so much about reaching other stars? Part of it is purely scientific curiosity. We want to know what's out there. We want to understand how common planets like Earth are, whether life exists elsewhere, what kind of worlds orbit different types of stars. These are legitimate scientific questions that can only be answered by going there and looking, but there's more to it than that. There's something deeply human about the urge to explore, to see what's over the next hill, to push boundaries and test limits. Our ancestors walked out of Africa and spread across the entire planet, crossing oceans and mountains and deserts to see what lay beyond. We've always been explorers. It's in our nature. Space is the ultimate frontier. It's the one environment that will never be fully tamed or domesticated. No matter how advanced our technology becomes, space will always be hostile to life. It's too cold, too empty, too filled with radiation. But that's part of what makes it compelling. It challenges us. It forces us to be clever, to innovate, to push the boundaries of what's possible. And there's beauty in the challenge itself. Think about the engineering required to build a spacecraft that can cross interstellar distances. Every component must be designed to function flawlessly for decades or centuries. Every calculation must be perfect because there's no way to send a repair crew. Every decision in the design process could mean the difference between success and failure. The people working on these problems are some of the smartest, most dedicated individuals our species produces. They spend years, sometimes entire careers, working on projects that might not come to fruition until long after they're gone. They do it because they believe it matters, because they want to be part of something larger than themselves, because they want to contribute to humanity's future. I find that incredibly inspiring. In a world often focused on short-term gains and immediate gratification, these people are thinking in terms of generations. They're working on problems whose solutions won't be known for decades or centuries. They're building the foundation for achievements that will be celebrated long after they're forgotten. There's a memorial at Kennedy Space Center that lists the names of astronauts who died in the pursuit of space exploration. It's a sobering reminder that exploration has always been dangerous, that pushing boundaries sometimes comes at a terrible cost. But those astronauts knew the risks. They chose to go anyway because they believed the goal was worth it. They believed that expanding humanity's reach, increasing our knowledge and inspiring future generations justified the danger. No one has died yet in the pursuit of interstellar travel, though people have certainly dedicated their lives to it. The scientists and engineers working on these problems might never see their work come to fruition, but they're building something that will outlast them. They're contributing to a legacy that spans generations. In a way, this is the most human thing we can do. We're the only species that thinks about its long-term future, that undertakes projects spanning multiple lifetimes. that builds cathedrals and plants olive groves knowing we won't live to see them completed. We think beyond our own brief existence. We dream of what could be, not just what is. And that's really what interstellar exploration represents. It's a dream, yes, but it's a dream grounded in reality, in physics and engineering and mathematics. It's a dream that's slowly becoming achievable, maybe not in my lifetime or yours, but possibly in our children's lifetimes or our grandchildren's. When that first probe finally reaches Proxima Centauri, when it sends back those first images of another star system, it will be a moment that transcends national boundaries and political divisions. It will be a human achievement, something our entire species can take pride in. It will be proof that we're capable of thinking beyond our immediate needs and wants, that we can work together on projects spanning generations. The images from that first interstellar probe will be studied for centuries. They'll appear in textbooks and museums. They'll inspire artists and poets and children who dream of stars. They'll be, in a very real sense, a message from our present to the distant future, saying, we did this, we reached out, we explored, we dared to dream that the stars were not forever beyond our reach. And who knows? Maybe those first images will show something unexpected. Maybe they'll reveal a world so interesting, so potentially habitable, that they inspire even greater efforts. Maybe they'll be the first step toward actual human missions to other stars, toward establishing humanity as a multi-stellar species. If you enjoyed this journey through the cosmos, it would mean the world to me if you subscribe to this channel and hit that thumbs up button. And if you made this far, I am sure you will love this other video at the left side of the screen. Why it's impossible for humans to travel 1 light year. 1 light year is an insurmountable wall. Discover why communication delays span years, how cosmic isolation shapes existence, and whether AI explorers replace human travel. See you there.